Okay, gather round if you want to hear this. This has got relations to what you're simulating at the moment. Anybody want to come round? It'll be on the web, but it probably won't be there until tomorrow afternoon, so which might be a bit too late for you by then. Okay, if I take a voltage source and I want that voltage source to drive a load, what do I already know about this that I didn't know before? How can I rephrase that slightly differently? If I put that across a resistor that has 0 ohms, in other words no resistance whatsoever, what do you think is going to happen to that circuit? Well, my assumption would be, based on what I know, that if I assume this is ideal, and an ideal voltage source will deliver whatever it says it's capable of doing, so assume it's 5 volts, I would assume that that could drive 5 volts into a short circuit. In other words, it would drive infinite current, a huge amount of current. That's what a voltage source is.
Assuming that there's no resistance in the wire.
Assuming there's no resistance in the wire, of course. Now, in an ideal world, and the point there is well taken, that there's no such thing as a 0 ohm resistor, because what you've got inside here, the thinner the piece of wire, like those little ones you're using there, you'd be hard pushed to get an amp through those. The thinner the piece of wire, the more resistance it has, especially when it gets hot. Now, what you're doing in your photopoppers is this. So you have a solar panel. So here's our solar panel. There's 2 wires coming off the back of it. And what happens there is that then goes, so one of these can go to ground, and the other one is going to go to one side of the capacitor. Like so, again, the best way, let's just do it this way. So that goes across your solar panel. One side's plus, one side's minus. What's going to happen now? The capacitor's going to charge. And we know the capacitor's going to charge. And it's going to charge, this is the one up here, or this is V in, which is what this is capable of generating. This is going to be 1 minus e to the minus t upon the time constant, which is going to be CR. Well, we don't really know what R is, but we know that the less light that falls on here, the slower this is going to charge. The more light falls on here, the faster it's going to charge. So what we have with this solar panel is we actually have a variable time constant. So 1, we know what 1 is, we know what E is, we know what T is because it's all on here. We don't know what tau is. And tau is CR or RC, whichever way around you want it. We know what C is because we put it in the circuit, but we don't know what R is. We can't really know R for all cases because it depends on how much light we've got on here. But this circuit works, the capacitor charges up, it's what you expect. You put it into the window, you put your oscilloscope across it, and you watch a lovely curve going up the screen just like this. And it reaches what's called its asymptote, which is here, which will be what the open circuit voltage of the panel is for that particular level of light. Can't exceed it because there's not enough input, and it might take a long time to get there if you haven't got much light. Okay, that's fine, right? So you're all comfortable with that, and you're building circuits which are firing according to the voltage threshold. So the cases we saw last week is we might say this is TH for our threshold. At that threshold, we want this circuit to dump, not everything, because it won't go right down to 0, but we want to dump as much as we can out of the capacitor and into a load, which is the robot doing some work. It moves, that's what we want it to do, right? So that's what the circuit is all about. The circuit is all about, so let's draw this in a slightly different way now. So turn the capacitor through 90 degrees. And now a more realistic diagram of what we have is this. So we're going into a capacitor like this, and we know this point here, the top of the capacitor. What's the bottom of the capacitor then? What's the voltage here? Well, that's a difficult one to answer actually, but for all intents and purposes, you can imagine that's ground that side. So I charge up and say my V in is 4.7 or something like that. So I'm heading towards 4.7. My circuit has been designed, say for 3.5 volts, something like that. So what that means is when this capacitor here reaches, say, 3.5 volts, what I want it to do is this. So I want it to operate a switch, so it's going to close that switch, which is going through a motor, and then once the voltage has dropped down, the motor is going to be turned off because the switch is going to open again. That's what you're building. Now, something that's caused a bit of confusion, consternation, whatever you want to call it, and we've seen more than once, is people trying to do this in a simulator. Now, we want a simulation. Definitely we want a simulation of this because it simulates quite well. What we've seen is people assuming that if we've got a voltage source here, plus and minus, that they can then connect this. Let's just call the rest of the circuit like this. The rest of the circuit. And out of here we have the load. Now, load is always going to look like a resistor of some description or an impedance of some description. And they've got this situation. But remember what happened before. We said that this voltage source could drive infinite current. So that doesn't model this. This is what we're trying to do. We're trying to say we want something in the simulation that looks a bit like a solar panel. We don't really have a solar panel in there. There is one of sorts, but the model's not set up for it and so on. So we want something that looks like the solar panel here charging into the capacitor. So the obvious thing to do there is say, well, this voltage source isn't ideal. We know it's not ideal. So we get an ideal one for inside multi-sim, but we put a resistor in the way. Okay, that's a completely different ball game now, because what we've now simulated, so this is, if you like, this whole thing now is your voltage source. But it's finite current. It means that that current is limited to that voltage source. So open circuit, if I don't connect anything to it, I should eventually still get my 5 volts coming out of there, or whatever this is. Say it is 5 volts here. I should still get 5 volts coming out of here if it's not loaded. What current can I make it drive? Well, you might like to take your solar panel and find out what the short circuit current of that solar panel is. Well, all you do for that is just put it through one of the multimeters on current, and you can see what the short circuit current is. But typically, I think something of the order of, say, 50 to 100 milliamps. Let's say 100 milliamps because it's a nice number to calculate. So if I assume that in this setup, the real setup, my solar panel will make 100 milliamps, I can simulate that because all I've really got to do, I know that this is V, I know that this is R, and I want to know the current. Well, V equals I times R. So by plugging those numbers in, I can work out what resistor I need to put in there to be able to simulate that solar panel. Now, what somebody did earlier, and well, 2 people actually, is they connected the rest of their circuit to here. Well, of course, that's no good, because that's the ideal voltage source, and it doesn't take a finite amount of time to charge up. It charges up infinitely quickly. So the output from your circuit has to be here to be able to simulate it. Now, also something that you need to take into consideration, because what people are doing, and many of the circuits are the same, so you've got your output chain, So here's your VCC, here's your ground. And what many people are doing is they've got a transistor here, which is a perfectly sensible thing to do. And they don't have a motor in multi-sim, so they use a resistor. Well, it peans, but by putting a resistor there, and if I turn that transistor on, current's going to flow from here down to here, isn't it? What do you think that's going to do to what I measure across here? So if I put a voltmeter across here, and I make this here greater than, so it's greater than 0.7 volts, which is when this is going to turn on, what do you think it's going to look like here? What do you think it's going to look like if this is off? So there's absolutely no current flowing down through the transistor. In other words, that connection's not there. What do you think it's going to look like across that voltmeter?
Yeah, the voltage is
To
quite
read that same value because it's in parallel. So the voltmeter will read the value that passes through the resistor because they're in parallel.
There are elements of truth in that.
Because no current is going
Will I measure a high voltage or will I measure a low
no
voltage?
ground now.
I'd say that
To read the output,
when you turn it on, you get a voltage spike and then it would settle back down to operating voltage.
Not for a fixed resistor, it would definitely have a fixed voltage to it for a fixed input voltage. But if I turn the transistor off, what would I measure across the resistor? Is there current flowing? Okay, so there you have it straight away. There's no current flowing, there's no volt drop, right? That's what V equals I times R refers to. It doesn't refer to voltage, it refers to volt drop. Okay, so if that transistor is off, we see no volt drop. On the things in multi-sim, you might see 10 nanoamps, or you might see 10 nanovolts or something. Well, clearly that's meaningless. Nano times 10 to the minus 9, it's just in the noise of the system. So I'd expect to see nothing in there. If I make this greater than 0.7 and this transistor turns on, current's going to flow down here and